Before you spread another bag of organic mulch, you need to understand the deadly paradox that destroyed my neighbor's vegetable garden last season. She followed every best practice: organic leaf compost, perfect 4-inch depth, proper spacing from stems. Yet her plants became magnets for flea beetles that seemed to appear overnight. The problem wasn't her technique. It was the hidden reaction between moisture-retaining mulch and pest-vulnerable plant varieties. I'll show you the specific plant chemistry markers that predict whether your varieties will resist or surrender to pest invasions. The truth behind this mulching disaster lies in understanding what the garden industry doesn't want you to know about their most recommended practices. Mulch manufacturers and extension services promote organic materials as natural pest deterrents that create protective barriers around plants while improving soil health. Agricultural supply catalogs feature testimonials from farmers crediting mulch applications with reduced pesticide usage and healthier crop yields. These marketing claims paint mulch as the foundation of integrated pest management systems. Research conducted at major agricultural universities reveals a disturbing contradiction to these promises. Controlled field studies comparing mulched plots to bare soil controls documented pest damage levels exceeding expectations by substantial margins. Scientists monitored identical plant varieties across multiple growing seasons, measuring pest populations and corresponding crop damage in both mulched and unmulched experimental plots. Mulched areas consistently harbored larger insect populations throughout the study period, with systematic patterns of increased feeding activity and reproduction rate. The explanation lies in understanding how organic mulch fundamentally transforms the microenvironment surrounding plant root systems. These changes create conditions that support rather than deter pest establishment and population growth. Moisture retention represents the most critical factor in this transformation process. Organic mulch layers function like biological sponges, absorbing precipitation and irrigation water while dramatically reducing evaporation rates from soil surfaces. Laboratory measurements demonstrate moisture increases ranging from 29 to 70% compared to bare soil conditions. This enhanced moisture retention creates ideal breeding environments for soil-dwelling insects that require consistent humidity levels for successful reproduction. Eggs deposited in mulched soil experience higher survival rates due to stable moisture conditions. Larval development accelerates under the protected, humid environment that organic matter provides. Temperature regulation compounds the moisture problem by maintaining consistently warm conditions throughout the root zone. Organic mulch layers insulate soil from daily temperature fluctuations that normally stress pest populations and disrupt reproductive cycles. The thermal stability allows insects to breed continuously rather than experiencing the natural population controls that temperature variations provide. Decomposing organic matter releases chemical compounds that function as attractants for specific insect species seeking feeding and reproduction sites. As microorganisms break down leaf litter, wood chips, and compost materials, they produce volatile organic compounds that insects detect through sophisticated chemical sensing systems. These decomposition byproducts essentially broadcast signals that advertise the availability of suitable habitat. The process creates a feedback loop where initial pest colonization accelerates decomposition rates through feeding activity and waste production. Increased decomposition generates additional chemical signals that attract more insects to the area. The mulch layer transforms from passive ground cover into an active pest recruitment system. Different organic materials produce distinct chemical signatures during decomposition, explaining why certain mulch types attract specific pest species while deterring others. Fresh wood chips release different volatile compounds compared to aged leaf compost or grass clippings. Understanding these chemical relationships becomes essential for predicting pest responses to mulching decisions. Regional variations in climate, soil composition, and native pest populations influence how these biochemical processes unfold. Areas with high humidity and warm temperatures accelerate decomposition rates and intensify the chemical attraction signals. Soil type affects moisture retention patterns, with clay soils retaining moisture longer than sandy compositions, potentially extending the period when conditions favor pest reproduction. The timing of mulch application relative to pest life cycles determines whether organic materials provide protection or create vulnerability. Early season applications may establish conditions that support pest reproduction before plants develop sufficient defenses. Material selection involves balancing pest management considerations with soil improvement goals, as fresh organic matter releases more volatile attractants compared to aged materials. Understanding these soil moisture dynamics reveals why identical mulching techniques produce dramatically different results across various garden environments. Success depends on recognizing when environmental conditions push moisture levels beyond the threshold where benefits transform into liability. The foundation for effective mulching strategies requires monitoring soil moisture levels and understanding how local climate patterns influence decomposition rates and pest activity cycles. This knowledge allows gardeners to time applications and select materials that maintain soil benefits while avoiding conditions that support destructive pest populations. Yet the moisture and chemical attraction problems represent only the beginning of mulch's hidden dangers. The very thickness that extension services recommend for optimal results creates an entirely different set of pest management challenges. Standard mulching protocols establish these conditions systematically across entire garden areas. Agricultural extension services recommend 4-inch thick organic layers as the foundation for moisture conservation and weed suppression. Master gardeners advocate continuous coverage from plant base to garden perimeter, creating seamless organic blankets that stretch across growing areas. Entomological research reveals that continuous mulch coverage functions like an elaborate transportation network designed specifically for pest movement and colonization. Instead of creating protective barriers, these organic layers establish protected corridors that facilitate rapid pest dispersal between feeding sites. The interconnected system allows insects to travel undetected while maintaining access to multiple host plants throughout the growing area. Flea beetles exploit mulch layers as tunnel systems that provide concealment during daylight hours and protection from natural predators. These insects emerge from organic matter during optimal feeding conditions, typically early morning and evening hours, when temperatures moderate and humidity levels peak. The mulch provides immediate refuge where beetles retreat after feeding, avoiding exposure to birds, spiders, and other biological control agents that patrol garden surfaces. During peak activity periods, flea beetles coordinate feeding patterns using chemical communication signals that travel through the mulch layer. Pheromone trails guide additional insects toward established feeding sites, concentrating pest pressure on already stressed plants. The organic matter amplifies these chemical signals by retaining volatile compounds in the humid microenvironment beneath the surface. Organic mulch materials offer dual benefits that support larger pest populations compared to bare soil environments. The decomposing matter provides alternative nutrition sources for insects during periods when preferred host plants become temporarily unavailable. Beetle larvae feed directly on organic debris while developing into adult forms, reducing juvenile mortality rates and accelerating population growth cycles. Mulch depth creates distinct stratified microclimates, where different insect species establish territories based on their specific environmental requirements. Surface layers support species that prefer moderate moisture and temperature fluctuations, while deeper levels harbor insects requiring consistent humidity and stable thermal conditions. This vertical habitat diversity allows multiple pest species to coexist within the same mulched area while minimizing direct competition for resources. The stratification enables coordinated feeding strategies where different species target various plant parts simultaneously. Root-feeding insects operate in deeper mulch layers, while leaf-feeding species work from surface positions. This coordinated approach maximizes damage potential by overwhelming plant defense systems through multiple attack vectors that occur simultaneously. The insulating properties of thick organic layers eliminate natural temperature fluctuations that normally disrupt pest reproduction cycles. Temperature stability accelerates pest generation times by providing optimal conditions for egg development, larval growth, and adult reproduction. Insects complete life cycles faster under mulched conditions, producing additional generations during single growing seasons compared to areas where temperature variations impose natural population controls. Different organic materials release distinct chemical signatures during decomposition that attract specific pest species. Wood chips produce compounds that appeal to certain beetle families, while aged leaf compost generates organic acids that attract different insect groups. Nitrogen-rich materials like grass clippings accelerate decomposition while producing compounds that attract insects requiring high-protein nutrition sources. The decomposition timeline influences pest attraction patterns throughout growing seasons. Fresh, organic matter produces immediate chemical signals that recruit initial colonizing insects, while aged materials provide sustained habitat that supports established populations. Managing decomposition rates through material selection affects pest colonization success. Recognizing mulch as active habitat rather than passive protective barrier fundamentally transforms strategic approaches to garden management. Traditional thinking assumes organic ground cover functions primarily as physical protection, while ecological reality demonstrates that mulch creates complex biological systems that either support or suppress pest populations depending on implementation strategies. Strategic mulch gap implementation disrupts continuous pest movement corridors while maintaining soil benefits in targeted areas around valuable plants. Creating deliberate breaks in mulch coverage forces insects to traverse exposed soil zones where they become vulnerable to predation and environmental stresses. Material selection strategies can maintain soil improvement benefits while incorporating pest deterrent properties through careful consideration of decomposition chemistry and habitat characteristics. Understanding these mulch-mediated pest dynamics reveals why identical gardening techniques produce dramatically different results across various plant varieties. The success or failure of mulching strategies depends not only on environmental conditions and application methods, but on the fundamental biochemical characteristics of the plants themselves. Certain varieties possess inherent traits that determine whether they thrive or perish under the complex conditions that organic mulch creates. A comprehensive field experiment using amaranth as the primary test crop uncovered the complex biochemical processes occurring beneath organic mulch layers that determine plant survival outcomes. Agricultural researchers selected amaranth varieties specifically because this crop family demonstrates exceptional adaptability across diverse growing conditions while maintaining reputation for natural pest resistance. Through indigenous cultivation methods, the crop's genetic diversity and established pest tolerance made it an ideal candidate for isolating the specific factors that influence mulching success rates. Research protocols established identical growing conditions across experimental plots, with amaranth varieties planted in both mulched and unmulched sections to eliminate environmental variables that might influence results. Each plot received identical soil preparation, irrigation schedules, and nutrient applications to ensure that mulch presence remained the primary experimental variable. The controlled environment allowed researchers to attribute observed differences directly to mulch-induced changes rather than variations in cultivation practices. Identical amaranth cultivars demonstrated radically different survival patterns when subjected to mulched versus unmulched growing conditions. Plants that thrived in bare soil environments experienced severe stress and damage when organic mulch surrounded their root systems. The contrast revealed that mulching effects depend heavily on plant-specific characteristics rather than universal environmental benefits that gardening publications commonly describe. Experimental design tracked Dissonychia glabrata flea beetle populations across multiple amaranth varieties throughout complete growing seasons. These specialized insects serve as indicator species because their feeding preferences and reproduction patterns respond predictably to environmental changes. Population monitoring involved weekly counts of adult beetles, egg clusters, and feeding damage assessments to establish comprehensive data on pest pressure variations between treatment groups. Beetle population densities in mulched experimental plots consistently measured 60% higher compared to unmulched control areas, with corresponding increases in measurable leaf damage across all monitored time periods. The elevated pest populations correlated directly with enhanced reproduction rates facilitated by the stable moisture and temperature conditions that organic mulch creates. Higher survival rates among juvenile beetles contributed to accelerated population growth cycles that compounded throughout growing seasons. Feeding damage assessments documented the progression from initial pest colonization through complete plant destruction in susceptible varieties. Early feeding activity concentrated on young leaf tissues, gradually expanding to include mature foliage as beetle populations increased. Damage patterns revealed systematic feeding strategies where insects targeted specific plant tissues based on nutritional content and defensive compound concentrations. Certain amaranth varieties demonstrated extreme vulnerability to mulch-induced pest pressure, with green callaloo cultivars suffering severe defoliation as beetle populations overwhelmed their defensive capabilities. Plants that maintained healthy growth in unmulched conditions became unable to recover from feeding damage when organic matter surrounded their root systems. The dramatic transformation from healthy plants to destroyed crops occurred despite identical cultivation practices across all experimental treatments. Complete defoliation events progressed through predictable stages as pest populations overwhelmed plant defensive capabilities. Initial feeding damage triggered stress responses that reduced plant vigor and compromised natural resistance mechanisms. Weakened plants became increasingly vulnerable to additional feeding pressure, creating cascading effects that led to total crop failure. Meanwhile, specific varieties, including Molten Fire and Hopi Red Dye, maintained robust growth patterns despite identical mulch treatments and equivalent initial pest pressure levels. These resistant cultivars demonstrated remarkable tolerance for the environmental conditions that proved devastating to susceptible varieties. The contrast highlighted genetic variations that determine individual plant responses to mulch-induced challenges. Resistant varieties exhibited feeding damage patterns that remained localized to specific leaf areas without spreading to encompass entire plants. Beetles feeding on these cultivars showed reduced reproduction rates and decreased survival compared to insects feeding on susceptible varieties. The plants maintained sufficient photosynthetic capacity to support continued growth despite ongoing pest pressure. Growth rate comparisons revealed that resistant varieties actually benefited from mulch applications when pest pressure remained manageable. Enhanced soil moisture and nutrient availability supported accelerated development in plants capable of withstanding beetle feeding activity. The environmental benefits of mulching became apparent only when plant genetics provided adequate defensive capabilities. Biochemical analysis revealed that survival differences between resistant and susceptible varieties traced directly to measurable concentrations of specific defensive compounds present in leaf tissues. Laboratory testing identified distinct chemical profiles that correlated with pest resistance levels across all experimental varieties. The chemical composition of plant tissues determined whether mulch-induced pest pressure resulted in plant death or manageable feeding damage. Leaf protein content emerged as a primary factor in determining pest feeding preferences and reproduction success rates. Higher protein concentrations created compounds that reduced palatability while interfering with insect digestive processes. Beetles demonstrated clear preferences for low-protein plant tissues when multiple varieties remained available for feeding selection. Polyphenol compound analysis revealed additional chemical defense mechanisms that influenced pest survival and reproduction outcomes. These complex organic molecules function as natural pesticides that disrupt beetle reproductive cycles and reduce feeding efficiency. Varieties with elevated polyphenol levels consistently showed reduced pest damage across all experimental conditions. The correlation between specific biochemical markers and pest resistance provided definitive evidence that plant chemistry determines whether mulching strategies succeed or fail. Laboratory analysis revealed that identical-looking amaranth varieties contained vastly different concentrations of these critical defensive compounds. Understanding these chemical variations requires examining how plant biochemistry creates sophisticated molecular defense systems that determine pest feeding success. Flea beetles and related species possess specialized chemoreceptors that detect specific compounds within plant tissues before committing to extended feeding activities. These sensory systems allow insects to distinguish between nutritionally suitable hosts and plants containing deterrent chemicals that could impair their survival or reproductive success. Chemical analysis conducted on amaranth samples revealed dramatic variations in defensive compound concentrations between varieties that appeared virtually identical in terms of visual characteristics, growth patterns, and general vigor. Standard morphological assessments failed to predict which plants would resist pest pressure, while biochemical testing provided reliable indicators of defensive capacity. The disconnect between visual appearance and chemical content explains why gardeners experience unexpected failures when applying uniform mulching strategies across different plant varieties. Protein content within leaf tissues functions as the primary determinant of palatability for flea beetles and similar foliage-feeding insects. Higher concentrations of leaf proteins create compounds that generate unpalatable feeding experiences, forcing beetles to abandon established feeding sites in search of more suitable nutrition sources. These protein structures bind with insect taste receptors, triggering rejection responses that override feeding instinct. Protein-rich plants, they also require greater energy expenditure for insects to process consumed material into usable nutrients. Beetles feeding on high-protein foliage experience reduced feeding efficiency, requiring longer feeding periods to obtain equivalent nutritional value compared to low-protein alternatives. Extended feeding times increase exposure to predation risks and environmental stresses, creating additional survival pressures that discourage sustained colonization. The digestive burden imposed by high-protein plant tissues reduces reproductive capacity among beetles that persist in feeding despite palatability challenges. Female beetles consuming protein-rich foliage produce fewer viable eggs compared to those feeding on easily digestible alternatives. Reproductive success rates decline as energy allocation shifts from egg production toward digesting complex protein molecules. Research measurements demonstrated that molten fire amaranth, which recorded the highest protein concentration at over 21,000 micrograms per milliliter, experienced minimal pest damage compared to low-protein cultivars when grown under identical mulched conditions. The correlation proved consistent across multiple growing seasons and diverse environmental conditions, establishing protein content as a reliable predictor of pest resistance in mulched garden systems. Polyphenol compounds represent the secondary defense system that operates through direct toxic effects on insect physiology and reproductive processes. These complex organic molecules function as natural pesticides, disrupting cellular processes within beetle digestive systems, while interfering with hormone production required for successful reproduction. Polyphenols bind with insect enzymes, preventing proper nutrient absorption and creating systemic stress that reduces survival rates. Consumption of polyphenol-rich plant material triggers oxidative stress responses within beetle cells, damaging cellular structures and impairing normal metabolic functions. The oxidative damage accumulates over successive feeding cycles, eventually leading to reduced longevity and compromised reproductive output. Insects exposed to high polyphenol concentrations experience shortened lifespans that limit their capacity to establish persistent populations. Statistical analysis across all test varieties and growing conditions confirmed that polyphenol concentration correlates significantly with pest resistance levels. Molten Fire and Hopi Red varieties, which recorded the highest polyphenol content at over 4 milligrams gallic acid equivalent per 100 grams, consistently demonstrated reduced beetle colonization rates, lower reproductive success among established pest populations, and faster recovery from initial feeding damage. The relationship remained stable across diverse environmental conditions and pest pressure levels. Polyphenol effectiveness depends on specific molecular structures and concentrations rather than total compound presence. Certain polyphenol types provide superior defensive benefits compared to others, with condensed tannins and flavonoid compounds demonstrating particularly strong pest deterrent properties. Chemical analysis must distinguish between polyphenol types to accurately predict defensive capacity. These chemical defense mechanisms explain why certain plants actually derive benefits from mulch-induced environmental stress, while others collapse under identical growing conditions. Plants with robust defensive chemistry can exploit enhanced soil moisture and nutrient availability provided by mulch applications without succumbing to increased pest pressure. Susceptible varieties lack sufficient chemical defenses to counteract the elevated pest populations that mulched environments support. Defensive compound interactions create synergistic effects where proteins and polyphenols work together to provide comprehensive protection against pest establishment and population growth. Plants possessing both high protein content and elevated polyphenol concentrations demonstrate superior resistance compared to varieties excelling in only one defensive category. Understanding these biochemical profiles enables accurate prediction of mulching outcomes before investing significant time and resources in potentially counterproductive garden management strategies. However, Translating this chemical knowledge into practical variety selection decisions requires examining how different cultivars perform under real-world mulched conditions. Traditional gardening publications devote extensive coverage to mulch material selection, application depth measurements, and seasonal timing strategies, while consistently overlooking the fundamental factor that determines success or failure in mulched garden systems. Master gardener programs teach precise techniques for spreading organic matter, calculating coverage areas, and maintaining proper distances from plant stems. Agricultural Extension Services publish detailed guides comparing wood chips, leaf compost, and grass clippings based on decomposition rates and nutrient release patterns. The critical oversight in conventional mulching advice centers on plant variety selection as the primary determinant of pest resistance outcomes. Standard recommendations assume that proper application techniques will produce consistent results across all plant varieties within specific species categories. The assumption ignores genetic variations that create dramatically different defensive capabilities between closely related cultivars. Genetic differences in defensive compound production create the fundamental distinction between varieties that thrive under mulched conditions and those that face complete destruction from identical environmental pressures. Plant breeding programs have selected for various characteristics, including yield, appearance, and disease resistance. But pest resistance under high moisture conditions rarely receives consideration during variety development processes. The genetic programming that controls protein synthesis and polyphenol production operates independently of visible plant characteristics, meaning that varieties with similar appearance and growth patterns can possess vastly different biochemical defense systems. Laboratory analysis remains the only reliable method for determining defensive compound concentrations before committing to specific varieties in mulched garden applications. Molten fire amaranth established itself as the superior performer across all experimental trials, maintaining elevated protein concentrations while demonstrating minimal pest damage despite sustained beetle pressure throughout growing seasons. The variety's robust defensive chemistry enabled it to exploit the enhanced moisture and nutrient conditions that mulch applications provide without succumbing to the increased pest populations that those same conditions support. Consistent performance data revealed that molten fire plants sustained damage scores consistently below 1.2 on the research scale, representing less than 20% leaf damage even when beetle populations reached peak density levels in surrounding mulched areas. The variety maintained sufficient photosynthetic capacity to support continued growth and development despite ongoing pest pressure. Recovery rates from feeding damage exceeded those of all other tested varieties by substantial margins. The biochemical analysis of molten fire tissues revealed protein concentrations exceeding 21,000 micrograms per milliliter, the highest levels recorded among all tested varieties and well beyond the threshold required for effective pest deterrence. Polyphenol levels measured similarly elevated, providing synergistic protection that reinforced the protein-based defensive mechanisms. The combination created comprehensive protection against multiple pest attack strategies. Red garnet and Hopi red dye varieties demonstrated intermediate resistance capabilities, experiencing moderate pest damage while maintaining sufficient recovery capacity to survive mulched growing conditions. These cultivars absorbed initial beetle feeding pressure without collapsing, then regenerated damaged tissues once pest populations declined due to reduced food quality and availability. Intermediate resistance varieties typically sustained damage scores between 2.0 and 3.0 during peak pest activity periods, but recovered sufficient photosynthetic capacity to complete growing cycles successfully. The damage patterns remained localized rather than spreading systematically across entire plants, indicating defensive compounds concentrated in specific tissue types. Green callaloo and red leaf varieties proved catastrophically vulnerable to mulch-induced pest pressure, consistently recording damage scores between 3.6 and 3.8, representing 70 to 90% of total leaf mass lost to concentrated flea beetle feeding in mulched experimental conditions. These susceptible cultivars lacked sufficient defensive chemistry to deter initial pest colonization or limit feeding damage once beetles established feeding sites. Complete defoliation typically occurred within 3 to 4 weeks of initial pest discovery, proceeding through predictable stages as beetle populations overwhelmed inadequate plant defenses. The rapid progression from healthy plants to destroyed crops demonstrated the critical importance of defensive compound concentrations in determining survival outcomes. The comprehensive ranking system incorporated multiple performance metrics, including total leaf damage assessment, sustained insect population counts, overall biomass yield measurements, and tissue recovery rates to establish definitive variety performance hierarchies. The multi-factor evaluation provided robust data for identifying superior performers across diverse growing conditions and pest pressure levels. These variety-specific response patterns indicate that effective mulching strategies require customization based on individual plant genetics rather than universal application of standard techniques across diverse cultivars. The genetic lottery of defensive compound production determines whether plants will benefit from or succumb to mulch-induced environmental changes. Selecting varieties with proven biochemical resistance transforms mulch applications from potential garden disasters into valuable soil management tools that support robust plant growth while maintaining pest pressure at manageable levels. However, even resistant varieties require careful monitoring to ensure that changing environmental conditions do not shift the balance toward pest establishment and population growth. Successful monitoring systems distinguish between manageable environmental fluctuations and conditions that signal impending pest disasters. Most gardeners discover problems only after extensive damage has already compromised their plants, transforming manageable issues into garden disasters that require drastic intervention measures or complete crop replacement. Traditional garden monitoring focuses on visible symptoms like wilted leaves, stunted growth, or obvious insect presence, but these indicators appear weeks after the underlying conditions have already established favorable environments for pest reproduction and population expansion. Late-stage detection leaves limited options for effective intervention since pest colonies have already reached sustainable population levels. Early warning systems detect environmental and biological changes that precede visible plant damage by substantial time periods, providing crucial intervention windows when corrective measures remain highly effective. The key lies in recognizing subtle indicators that signal developing problems before they escalate into irreversible damage pattern. Soil moisture monitoring represents the most critical early detection tool for preventing mulch-induced pest disasters. Digital moisture meters provide precise measurements that reveal when soil conditions cross the threshold from beneficial to problematic for pest establishment. Regular monitoring establishes baseline moisture patterns that help identify when conditions shift toward pest-favorable environments. Research demonstrates that elevated moisture levels maintain the humid microenvironments that support continuous breeding while extending insect survival rates during vulnerable developmental stages. The correlation between increased soil moisture and accelerated pest reproduction appears consistently across diverse environmental conditions, though specific threshold levels vary based on soil composition and local climate patterns. Heavy clay soils retain moisture longer after irrigation or precipitation events, creating extended periods when conditions favor pest reproduction. Sandy soils require more frequent monitoring since moisture levels fluctuate rapidly with weather patterns. Visual inspection protocols focus on specific plant tissues where initial pest activity concentrates before spreading to more visible areas. Lower leaves provide the first indication of flea beetle colonization through characteristic feeding patterns that differ from damage caused by other common garden pests. The feeding signatures appear as small, irregular holes that penetrate completely through leaf tissues rather than creating surface scarring or edge damage. These distinctive hole patterns result from flea beetle feeding behavior, where insects consume small circular sections of leaf material, leaving clean perforations surrounded by healthy tissue. The holes typically measure 2 to 4 millimeters in diameter with smooth edges that distinguish them from ragged damage caused by caterpillars or other chewing insects. Fresh holes appear bright green or pale yellow around edges before aging to brown margins. Initial feeding damage concentrates on tender lower leaves where humidity levels remain highest and plant defensive compounds occur in lower concentrations. Beetles prefer these protected feeding sites that offer optimal nutrition while minimizing exposure to environmental stresses and predation risks. Early detection requires systematic inspection of lower foliage areas that gardeners typically overlook during casual garden surveys. Dawn inspection periods reveal insect activity patterns that remain hidden during typical daytime garden visits. Flea beetles demonstrate peak activity during early morning hours, when temperature and humidity conditions optimize feeding efficiency. Unusual insect movement around mulch edges during these periods indicates established colonies preparing for daily feeding cycles. Multiple insects moving simultaneously suggest coordinated colony activity rather than isolated individual behavior. Concentrated activity around specific plants indicates established feeding preferences and colony establishment. Peak activity typically occurs within the first 2 hours after sunrise, when environmental conditions provide optimal protection for exposed insects moving between shelter and feeding sites. Plant health indicators reveal physiological stress responses that develop before obvious pest damage becomes apparent to casual observation. Yellowing patterns that begin with lower leaves and progress upward through plant canopies suggest combination effects from excessive soil moisture and early pest feeding pressure. The yellowing differs from nutrient deficiency symptoms by appearing first in areas with highest humidity exposure. Stunted growth patterns in previously vigorous plants indicate root zone stress from sustained moisture levels that exceed optimal ranges for healthy development. Plants experiencing early moisture stress allocate resources toward root survival rather than continued foliage expansion, creating visible growth reduction before pest damage becomes obvious. Growth rate comparisons with baseline measurements reveal developing problems weeks before severe symptoms appear. Understanding these warning indicators enables implementation of corrective measures while pest populations remain manageable and plant recovery capacity stays intact. Early intervention strategies prove significantly more effective than reactive treatments applied after pest establishment reaches damaging levels. Systematic monitoring protocols, combining moisture measurement, visual inspection, and behavioral observation, provide comprehensive early detection systems that prevent minor pest issues from escalating into complete garden failures. Weekly assessment schedules generate sufficient data for tracking developing trends while allowing time for effective intervention strategies. The monitoring approach transforms garden management from reactive crisis response to proactive problem prevention, maintaining healthy growing conditions while avoiding the environmental extremes that support destructive pest populations. Yet the critical question remains: at what precise point do beneficial moisture conditions transform into pest breeding facilities that overwhelm even resistant plant varieties? Laboratory research conducted across multiple experimental sites revealed the existence of critical moisture relationships that determine whether organic mulch functions as protective ground cover or transforms into active pest breeding facilities. Precise soil moisture measurements using calibrated electronic sensors identified specific pattern where pest populations shift from manageable levels to exponential growth that overwhelms plant defensive capabilities. Soil moisture has been universally regarded as beneficial for plant development, with agricultural practices consistently emphasizing water retention as a primary objective for healthy crop production. Irrigation systems, mulching techniques, and soil amendments focus on maximizing moisture availability to support robust root development and sustained plant growth throughout growing seasons. Extension services recommend consistent soil moisture levels as fundamental requirements for successful gardening across diverse climate conditions. Research measurements demonstrated a clear correlation between elevated soil moisture levels and increased pest populations across all experimental locations. Mulched experimental plots consistently recorded gravimetric moisture content of 36% compared to significantly lower levels in unmulched control areas. The enhanced moisture retention created environmental conditions that supported larger pest populations while simultaneously creating stress conditions that compromised plant defensive chemistry. Below moderate moisture levels, experimental plots with organic mulch coverage demonstrated pest population levels statistically equivalent to unmulched control areas, indicating that normal ecosystem balance mechanisms remain functional when soil saturation stays within reasonable ranges. Beneficial insect populations maintain adequate predation pressure on pest species, while environmental stresses prevent unlimited pest reproduction. Plant defensive systems operate effectively under these conditions, maintaining resistance to pest colonization attempts. Moderate moisture levels represent the range where mulch benefits, including improved soil structure, enhanced nutrient availability, and consistent root zone hydration, occur without triggering the environmental conditions that support pest population explosions. Plants grown under these moisture conditions access enhanced growing conditions while maintaining natural pest resistance mechanisms that prevent significant significant crop damage. As soil moisture levels increase beyond moderate ranges, gradual increases in pest populations begin appearing across experimental plots, accompanied by early stress symptoms in susceptible plant varieties. This transitional moisture range creates increasingly favorable conditions for pest establishment, while beginning to compromise plant vigor through excess soil saturation. Initial pest colonization occurs during this phase, establishing the foundation populations that later expand rapidly when moisture levels increase further. Susceptible varieties demonstrated visible stress indicators, including slight yellowing of lower leaves, reduced growth rates, and decreased defensive compound production during exposure to elevated moisture levels. The physiological stress weakens natural resistance mechanisms, making plants increasingly vulnerable to pest-feeding pressure. As environmental conditions continue favoring insect reproduction over plant defense systems. Under consistently high soil moisture conditions, flea beetle reproduction accelerated dramatically throughout all experimental locations, with generation times shortened compared to reproduction rates measured under normal moisture conditions. The accelerated reproduction creates multiple overlapping generations within single growing seasons, producing exponentially larger pest populations that overwhelm even resistant plant varieties through sheer feeding pressure volume. The shortened generation times result from optimal temperature and humidity conditions that support continuous egg development, larval growth, and adult maturation, without the environmental stresses that normally extend developmental periods. Stable moisture levels eliminate the population bottlenecks that typically occur when soil conditions fluctuate between wet and dry periods throughout growing seasons. Female beetles exposed to optimal moisture conditions produce larger egg clutches with higher survival rates, while shortened development times allow multiple reproduction cycles where normal conditions support only single-generation completion. The compounding effect of increased egg production and shortened generation times creates exponential population growth that quickly exceeds plant tolerance thresholds. Soil composition influences how rapidly moisture levels reach problematic ranges, with clay soils achieving high saturation faster than sandy compositions due to fundamental differences in water retention characteristics. Heavy clay particles bind moisture molecules more effectively than larger sand particles, creating sustained high moisture conditions that persist longer after irrigation or precipitation events. Sandy soils require higher water inputs to reach critical moisture levels, but also drain more rapidly when water sources diminish. The drainage differential affects pest establishment patterns by determining how long soil conditions remain optimal for insect reproduction. Clay soils provide extended periods of optimal breeding conditions, while sandy soils create shorter but potentially more intense pest pressure periods. Understanding soil-specific moisture dynamics enables prediction of pest risk periods throughout growing seasons. This moisture correlation provides the explanation for why identical mulching techniques produce completely different outcomes across various geographic regions, seasons, and garden locations. Areas experiencing consistent rainfall or high humidity reach elevated moisture levels readily, while arid regions rarely achieve the soil saturation necessary for pest population explosions. Seasonal variations in precipitation patterns determine when pest pressure peaks occur relative to plant growth stages. Regional success patterns correlate directly with average soil moisture levels during peak growing seasons, explaining the geographic distribution of mulching success stories versus failure reports. Monitoring soil moisture levels throughout growing seasons enables gardeners to maintain the beneficial aspects of mulch applications while preventing soil conditions from crossing into pest-favorable territory. Understanding these moisture relationships reveals that successful mulching requires more than simply following standard application techniques across all garden situations. Innovative mulching approaches eliminate pest establishment risks while maintaining the essential soil health benefits and moisture conservation properties that make organic ground cover valuable for garden productivity. These advanced strategies recognize that traditional methods create favorable conditions for pest reproduction while still delivering the fundamental advantages that gardeners seek from mulch applications. Traditional continuous mulch coverage establishes the specific environmental conditions that support rapid pest colonization and population growth throughout growing seasons. Standard application techniques create uninterrupted organic matter layers that function as protected corridors for insect movement while maintaining optimal breeding environments. Alternative strategies disrupt these favorable conditions while preserving soil improvement benefits through strategic placement modifications, material selection criteria, and timing adjustments. Strategic placement techniques, selective material choices, and precise timing modifications prevent pest establishment while preserving the moisture retention, nutrient cycling, and soil structure improvements that justify mulching investments. These approaches require understanding pest movement patterns, reproduction cycles, and environmental preferences to design systems that maintain benefits while eliminating risks. Ring mulching creates targeted beneficial microclimates around individual plants while establishing pest-disrupting gaps between growing areas that prevent continuous pest movement corridors. This technique applies organic mulch in circular patterns surrounding plant bases, leaving unmulched strips between different growing zones. The gaps force insects to traverse exposed soil areas where they become vulnerable to predation and environmental stresses that limit population establishment. The ring approach maintains soil moisture conservation directly around plant root zones, where benefits provide maximum value, while eliminating the continuous pathways that enable rapid pest dispersal between vulnerable plants. Individual rings can be customized based on plant size, water requirements, and specific pest susceptibility factors without compromising overall garden management efficiency. Ring applications typically extend 18 to 24 inches from stem bases for most vegetable crops, with gaps of 12 to 18 inches between rings, providing sufficient disruption to pest movement while allowing practical garden maintenance access. Gravel and inorganic mulches deliver moisture conservation and comprehensive weed suppression benefits without creating the decomposing organic matter that supports pest population growth and reproduction cycles. These materials reflect heat rather than creating humid microclimates, while providing physical barriers that prevent weed establishment without supporting insect breeding activities. Gravel applications require proper soil preparation, including landscape fabric installation, to prevent material migration into soil layers. Decorative stone options include river rock, crushed granite, and recycled concrete materials that complement garden aesthetics while providing consistent performance throughout multiple growing seasons. Inorganic mulch longevity exceeds organic alternatives by substantial margins, eliminating annual replacement costs while providing consistent performance. The materials resist decomposition, maintain stable coverage depths, and require minimal maintenance beyond periodic cleaning to remove accumulated debris. Seasonal mulching applies organic materials during pest inactive periods while removing them during peak reproduction seasons. Timing applications to maximize benefits while minimizing pest exposure window. This approach requires understanding local pest life cycles and seasonal activity patterns to optimize application and removal schedules. Spring applications occur after soil temperatures stabilize, but before pest emergence periods, providing early season moisture conservation while avoiding peak reproduction timing. Late season applications support beneficial soil organisms during winter months, when most pest species remain dormant or inactive. Removal timing correlates with pest emergence patterns identified through local extension service data or historical garden observations. Temporary storage systems allow removed materials to compost separately before reapplication during subsequent low-risk periods. Layered mulching systems combine different materials to create pest deterrent surfaces positioned over soil-improving base layers. Base layers consist of fine organic materials that decompose slowly and improve soil structure, while surface layers utilize pest-repelling materials that discourage colonization. The combination maintains moisture retention and nutrient cycling while eliminating surface conditions that support insect breeding activities. These alternative strategies demand more comprehensive planning than traditional continuous mulching techniques, requiring analysis of local pest cycles, plant variety selection, and seasonal timing coordination. The additional planning investment produces superior results in environments where standard mulching approaches consistently fail due to pest pressure problems. Implementation success depends on matching specific techniques to local garden conditions. plant varieties, and regional pest populations rather than applying universal solutions across diverse situations. Ring mulching offers the most accessible starting point for gardeners seeking immediate improvements, while seasonal timing strategies require minimal equipment investment beyond basic planning. Effective mulch strategy selection requires evaluating soil type, drainage characteristics, predominant pest species, and seasonal climate patterns to identify optimal approaches for specific growing environments. The systematic approach produces predictable outcomes that support garden productivity goals while maintaining ecological balance. These practical solutions transform mulching from unpredictable gardening gambles into reliable soil management tools that deliver consistent benefits while eliminating destructive pest establishment risk. The key lies in recognizing that garden management involves complex biological relationships that extend far beyond simple application techniques. Understanding these biological relationships transforms mulching from unpredictable gardening techniques into reliable soil management systems. The mulching paradox demonstrates that successful garden management requires understanding the intricate relationships between soil moisture dynamic, plant biochemical defense systems, and pest ecological patterns, rather than applying universal techniques across diverse growing environments. Your next mulching decision should begin with 3 critical steps: comprehensive soil moisture monitoring, strategic variety selection based on defensive compound concentrations, and implementation of alternative placement strategies that disrupt pest corridors while maintaining soil benefits. These foundational considerations determine whether mulching strategies support or undermine garden productivity goals through their effects on pest establishment patterns. The most actionable takeaways center on variety selection importance, moisture threshold monitoring, and strategic mulching approaches that eliminate continuous pest highways while preserving soil improvement benefits. What surprised you most about these hidden connections between mulch applications and pest pressure dynamics?